Welcome. So let us discuss one more kind of bond, which is metallic bond. And it's a short discussion. So let us share this video while discussing this topic.
Metallic crystal, very similar to the organization, and that keeps
we
the
have
crystal.
Understood before from ionic bond chapter that ionic bond is formed between cation, positive charge, and anion. So this positive charge cation and the negative charge anion rearrange itself to form a crystal. So it is obvious the attraction between negative and positive is due to electrostatic attractions. But if we have
crystal together, let's look at the arrangement of atoms in a metallic crystal. Very similar to the organization of an ionic crystal.
So if we look at the metallic crystal, okay, it's all positive in charge. So how do these crystals form? What is the attraction between this positive charge? Logically is if you have the same charge, then it should repel each other. But we'll see.
However, they're all positively charged, and just looking at this illustration, you would think that the atoms would completely fly apart by repelling each other due to the positive charge. But if we take a closer look, the electron C model tells us how the positively charged cations in the metallic crystal can stay together. So as an example, we'll take a look at aluminum. Looking at the subatomic structure, we can see each aluminum atom has 13 protons, but only 10 electrons. It has given up the 3 valence electrons.
Okay, so you can see now is the metal, which is aluminium. It has given up 3 of its valence electron to the sea of electron.
To what is called the electron C. This is why it's called the electron C model. The space in between each atom is filled by the valence electrons that have been given up by each metal atom. So the metal atoms become cations, positively charged ions, and the valence electrons are loose in the spaces between the cations. So what's holding the crystal?
So the valence electrons are loose in between the metal atoms in a sea of electrons. So they share a sea of electrons from valence of each aluminium atom.
Crystal together is the electrostatic attraction between the positively charged cations and these free-floating negatively charged electrons.
So the metallic bond is actually between the positively charged and the negatively charged electron in the sea of electron.
So the valence electrons are not localized to any one particle. They are free to move and occupy the space between the positive ions. And so similar to the electrostatic attraction that holds the ionic crystal together, we have this attraction of opposite charges that are holding the metallic crystal together. So aluminum giving up 3 electrons means that all the cations have a 3+ charge, and each aluminum atom has contributed 3 electrons to the sea of electrons. This creates quite a strong